Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Hi, and welcome back to Driven. This is the first episode in a generative AI mini-series or mini-course, if you will, that I'm doing here on the Driven podcast. On the Driven Show website, there's a sequence of podcast episodes that form the basis of a mini-course on autonomous vehicles. But since AI has been sort of increasingly fundamental to everything we do these days, not just autonomous vehicles, but everything, and to this podcast, I thought I'd do something similar for it. So today we're going to start by talking about the smallest Lego piece in the AI universe, the artificial neuron. Now, when I say neuron, many of you might think of some squishy cell in your brain firing away, and that's not too far off. AI researchers actually borrowed the idea from the biological neurons in our head when we built these things. So over the course of this episode, we're going to explore exactly what an artificial neuron is, why it matters, how it sets the stage for everything else in AI. So get comfortable, grab a cup of coffee, fire up your own neurons, and let's dive right in. So first, let's talk about real neurons. Real neurons in our brains are these amazing magical cells, right? They communicate through electrical and chemical signals to other neurons. They communicate over things called axons and dendrites, right? Dendrites are sort of the inputs on neurons that receive signals from other neurons, and axons are outputs on neurons that transmit the signals away from the cell body to other neurons or target cells. So they branch out in every direction, forming these just vast networks with billions and billions of connections. So picture like a giant interwoven city of neurons all connected with these axons and dendrites, right? Actually, that would be a pretty horrifying thing to think about. Sort of like the Matrix, maybe. Anyway, artificial neurons, on the other hand, are a simpler mathematical abstraction of biological neurons that don't look nearly as messy. That is, if you don't think equations are messy and ugly. In its simplest form, researchers have kind of reduced all that biology into a tidy little formula like the following. Output equals activation function, which is a function of weights times inputs plus bias. That is, we take the input value coming into a neuron, we represent it as a number, which may be 0 or 1 as off or on. Maybe it takes on some negative value, or it's an analog value akin to like a voltage on some neuron. We'll get more into the specifics of that as we discuss deeper networks, but here we're keeping it kind of open as to what form these inputs can assume. And then there's a weight, another number multiplied by that input. And then the weight represents some value, like at the synapse, for example, of a neuron, where the dendrite connects and actually acts to positively reinforce or inhibit the input value, right? Multiply, amplify, or negatively de-amplify the value. So we have a multiplied value, the weighted input. Now, there'll be many of these inputs to a neuron, which are all weighted similarly, maybe hundreds or thousands in a modeled neuron. In a real neuron, there might be typically thousands of inputs. And then we sum up these weighted inputs and apply a bias in our artificial neuron model example. This will be some number to offset the resultant value by some amount, right? So now we have some biased input total that is the sum of the weighted inputs plus this bias that we give to it. And then we feed this into an activation function, which essentially determines if the sum of all these inputs fires the neuron or not based on the values that came in through these inputs, multiplied by the weights and considering a bias as well. It may be that if we're above some threshold, the neuron fires, or if we're below it, it doesn't. It could be as simple as that. Now, I realize this sounds like some piece of arcane, math, but it's actually a pretty neat trick that tries to mimic how a neuron might actually fire or not fire in a brain. The key takeaway here, the artificial neuron is inspired by biology, but nowhere near as complicated. It just does the same kind of pass-fail check when it fires based on the inputs it receives. You can think of this more simply as it takes some numbers and spits out another number. And yes, I just reduced decades of neuroscience to a single sentence, but that's it in a nutshell, or a neurocell, if you want to look at it like that. So how did this idea turn into something we actually use in computers? The neuron, as a distinct anatomical unit, was first clearly described by a gentleman by the name of Santiago Ramon y Cajal in the late 1800s. He was a Spanish neuroscientist. And he used Camilo Golgi's staining method to find that the nervous system is composed of discrete cells, neurons, rather than some sort of continuous blob of a network. Now, it was Emile Dubois-Reymond in the mid-1800s who demonstrated that nerves transmit electrical signals. And then there was this guy, Charles Scott Sherrington. I think I'm getting all these names right. In the late 1800s and early 1900s, he discovered that neurons communicate at junctions he termed synapses, where input signals are integrated before producing the output signals. Then in the 1930s and 40s, Alan Hodgkins and Andrew Huxley started to conduct some experiments, and they described more precisely how neurons generate electrical signals or action potentials in response to input stimuli. So on the heels of all this, in the 1940s, two researchers named Warren McCulloch and Walter Pitts were the first to propose the model of an artificial neuron. It was basically some big if statement. If the weighted sum of inputs is above some threshold, then output a 1. Otherwise, output a 0. But then in the 1950s came the idea of the perceptron, and that was conceived by a gentleman by the name of Frank Rosenblatt. It had a little more flair. It could actually learn and modify weights from data. It made some headlines back then, like the perceptron that can see, even though it was basically just classifying shapes. But all these steps mattered, right? Getting all these steps from the late 1800s, mid 1800s up until the mid 1900s, to go from what is a neuron just in our brain to actually starting to create artificial versions of this. And so putting that in perspective, humans have been around for hundreds of thousands of years, but in just the short span of like 100 years, we went from discovering the neuron to making artificial versions of it. And all of this laid the groundwork for the neural networks we use today, just another short step along the long and winding road of human history to get to the vastly more complicated things that we're doing now, just 70 years later after the first artificial neuron was conceived. So now let's break down the components of a single artificial neuron. The first is inputs. These are just numbers we feed into the neuron. So if you're building a model to detect, say, spam emails, each email word could be turned into a number somehow, like how often it appears, or maybe even some embedded code or hash as a function of the information that's received. And all those numbers get fed into this neuron. Again, the biological equivalents here are dendrites, right? Then there's weights. Each individual input gets multiplied by a weight, and you could think of the weights as like volume knobs. The bigger the weight, the more that input's going to matter. If your email has the word lottery in it, for example, we might crank up that weight because it's a strong sign of spam, right? So here the weights are like maybe like the chemical characteristics of a synapse in a real neuron, if you want to think of it like that. Then there's the bias. And after we multiply everything, we add this constant value we call the bias. And this is basically a trick that helps the neuron make decisions more flexibly. You can think of the bias as sort of like your secret spice blend that adds a little flavor to the final dish. But and honestly, I'm not sure if there's really a biological equivalent here, but I presume it would be like some chemical baseline level of a neuron if it did exist. Then there's the big decider, the activation function. It takes the sum of all these weighted inputs plus the bias and transforms it, often putting it into a certain range or flipping it on or off. Common activation functions are things like ReLU. You'll hear about that. It's the rectified linear unit, which basically says, hey, if the sum is negative, then I'm going to output a 0. If it's positive, just keep it as is. Others like the sigmoid or tanh functions squish the sum into a range between 0 and 1 or -1 and 1 respectively. And recall, though, an important point here is that the axon of a real neuron captures this output, right? So the activation function is going to basically determine which triggers the output value, which is the equivalent of sending some signal down the axon to other neurons. And so when you put it all together, you get something that can make a decision like, yes, this email is spam, or no, it's not. And that's really the essence of an artificial neuron with some highlights here about the biological equivalents along the way. Not too complicated, right? Well, what we'll see is that this simple fundamental element can yield amazingly complex pattern detection, generative content, and more when we stack a ton of these artificial neurons together. Not similar to what happens when real neurons, or not, I should say, dissimilar to what happens when real neurons are stacked together and connected throughout our brains. So I'm going to make this a little bit more concrete with a quick example of spam detection. Not very exciting, but we all experience and hate spam, so maybe it's a little relatable. So let's look at the inputs. So suppose we have 3 factors to detect spam. One is the frequency of the word 1. Another input might be the presence of a suspicious link, if we detect that. And then the third may be word count, right? So, and then for the weights, we might have a set of weights, let's say 5, 4, and -1, respectively. So that means we're giving a lot of importance to the word 1. We're giving it a 5 weight, right? And suspicious links as well. They're getting a weight of 4. But we actually penalize the total word count, right? We give that a -1 because maybe spam messages are short, so a longer email might be less suspicious. And then we have a bias. Let's say our bias is 2. That's like a little bump in the direction of more readily wanting to call something spam in this example. Finally, then there's the activation function. We feed this sum of the weighted inputs plus the bias into a function. Maybe it's that ReLU function that we talked about before, or the sigmoid. In this case, we say if it's above some threshold, we're going to say it's spam. And if it's below some threshold, we're going to say pass it through, it's all good, right? Now, in this simple example, single neurons, spam detection, you might be wondering, how does this relate to all the fancy AI that draws an elaborate picture of like a whale in space with Jimi Hendrix riding it playing guitar, or AI that writes code to create some brand new, video game, right? And the short answer is scale. Many, 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 many neurons, right? Massive networks of neurons. An artificial neuron by itself is pretty basic. But when you stack up thousands or millions of them, connecting the outputs of some to the inputs of others, you get these deep neural networks, right? That can start to recognize faces, translate languages, and even generate pictures of Jimi Hendrix riding whales in space, right? I think I'm going to work on that myself. It's kind of like a single Lego brick. By itself, it might not look like much. Maybe you can imagine it as a piece of a spaceship. But when you stack enough bricks together in just the right way, you can build the Millennium Falcon from Star Wars, right? So in a few episodes, we'll get to the part where we talk about deep networks and something called transformers. Those are basically these gargantuan families of neurons. But it all really starts here with the humble building block of a neuron. So that's the first episode in this Driven series of generative AI, starting with the neuron. It's simple, it's elegant, and it's the reason we can do all kinds of magical stuff in AI, neural network-based AI. In the next episode, we're going to talk about how we go from a single neuron to a small neural network, and we'll start to build upon that. We'll start to talk about forward pass and back propagation. These are not football terms, but these are all part of the secret ingredients that help these networks learn from mistakes and how learning occurs, right? If you found this helpful, stick around for the rest of the series. We're definitely on a journey here, and I'm on that journey with you, learning some new things along the way. Obviously, I've been doing neural networks for a long time with respect to automated vehicles and other robotics applications, but this generative AI is a new magical thing to all of us, right? So by the time we're done, you'll understand how generative AI can create text, code, images, and just a bunch of other things. So thanks for joining in. I look forward to exploring this topic with you in the next episode. Until then, go forth and mentally label all of your emails as spam or not spam, just for fun and practice. Till next time. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.